Okay, that sounds great.
Cool.
Here's
Um,
your slide.
yeah, so quick summary. We had a topic involving coronary artery calcium scans and their scores. So we reviewed what we covered in class, talking about how these scores are calculated, specifically how the Agatston score is calculated, and how the volume score is calculated, and sort of their pluses and minuses. We then discussed partial volume averaging and how that might change the scores themselves. And then we got into some mathematical models associated with how SNR is affected with changes in slice thickness of these coronary artery calcium scans. And then we showed a MATLAB simulation regarding sort of the partial volume averaging effect and how that changes the scores themselves. And we concluded that although the threshold of detection for these scores changes with slice thickness, it isn't necessarily important unless we can see real clinical benefit from these changes. And the scores themselves historically have been uh, extensively studied with thicker slices. So if that was to change, then likely that effect would need to be explored in a clinical setting. Um, and just the last thing, there is some existing clinical research regarding this, and they didn't see any improvement in their predictive models with these adjusted slice thicknesses.
Okay, just to clarify, their predictive models were the model that increasing Agatston score correlates to increasing numbers of events. Was that what their model?
Yeah, the Agatston score was involved with some other comorbidities, and there it was predictions of any acute coronary events.
Okay,
Yeah, so it was a part of the formula.
terrific. Okay, so one would conclude then that if you're looking at the entire range of Agatston score,
Mhm.
whether or not you use a thin slice, thick slice, it doesn't really matter because over that entire range, the size of the calcium is fairly large in most of those Agatston categories, right?
That is true. Yeah, if you're looking at the arteries themselves and how much calcium is present, it would have to be a real edge case to see one, the vessel being perfectly in plane with your slice, um, because that's the only scenario where your voxel ends up being tall for identifying that calcium. And also, the vessels themselves are normally larger than the voxels that and the slices that are currently used.
Okay. Did you did you I was interested in your model for the calcium. It's pretty cool that this ellipsoid that sits inside a bread loaf like that, and also the one that was a hemi, half of the vessel. That was a pretty sophisticated model. Some of the folks who asked questions had the same question that I did, was why did you choose something that was pretty big? Like why didn't you
I
go
can take this
down?
one.
Why didn't you go down to a level that
So we,
challenged the resolution?
yeah, we were looking at what is like a realistic calcium size that we would see in these sort of disease states. There isn't a whole bunch of literature on calcium volume. The one that we did find was actually like a uric acid study where they compared patients with elevated levels to low levels. And the average height of those calcified regions was like typically greater than 4 millimeters. So that's where we started with. That's why you see that kind of crescent-shaped one at 3.9 millimeters
Right,
was
right.
about normal. The lowest percentile was only like 1.9, 1.5 millimeters. So to Jacob's point, you're really getting towards edge cases when you get that small.
Yeah.
Um, we included those because I think it's good to model these edge cases, but that's why we didn't go super thin, like zero point 0.4 millimeters, for example.
Okay, so the your project then really was looking at reducing slice thickness and its effect on these fairly larger pieces of calcium, these things that you guys are calling them edge cases, but are fairly visible in all current 3 millimeter or 2.5 millimeter calcium scans. So let me ask you a question. Somebody who is 38, right, and goes in, and let's say we know their future. I can tell you their future, and I can tell you when they're 55, they're going to have an Agatston score of like 250. What do you think their Agatston score is when they're 38? And how big is the calcium?
Yeah,
I
I
mean, the
mean,
answer is that
yeah.
it's small and that
Yeah,
their score would be quite low. Um, and
good.
so if you're talking about the benefit of the predictive nature of putting them on, let's say, statins early on, certainly those smaller volumes will matter.
Right. So do you think that person who at 55 is going to have Agatston score 250, should they be on a statin when they're 40?
I'm not sure. The way that you described statins and their benefits in class makes me think yes, but I'm not sure.
That's a good answer because people probably don't know, right? Although they have a good notion. But studies like that are still to be done, right? If you find really early calcium and you treat it, does it further improve your ability to reduce the number of events, right? So, Tom, did you have any questions?
Yeah, just a quick question. So in the simulations, you sort of assumed ideal slice profiles and everything like that. What do you think, like if you actually simulated a multi-slice CT or the acquisition, would that have an effect on your conclusions at all?
Yeah, we had kind of struggled with how to implement these more sophisticated CT scan models. And I think the other group did some Gaussian blurring for the point spread function that we also considered for this as well. When we're looking at those kind of the lateral resolution of these, since that was held constant, um, I at least kind of justified it that those effects would be consistent through the range of slice thicknesses. If we started to do the whole multi-slice for the that that z-axis instead of the xy axis, um, I think that would also hold true as the slice thickness changed because that would be modeled. If we're taking zero point 0.6 millimeter slice, zero point 0.9 with the same model, we would still see a similar thing there. Um, if the modeling is consistent through the whole range.
So if we're comparing the difference between them, whether it has a point spread function or not, the difference will probably stay the same if both have it versus both don't.
Say that again. I'm sorry. Can you amplify that a bit?
Yeah, I guess the point being, if you make the simulation more realistic to what CT looks like, and you are doing a comparison between two different slice thicknesses,
Hmm.
the comparison is your comparison would be the same if both have point spread functions versus both don't, because you're evaluating the difference between them, not sort of how they individually affect your HU scores.
So you're assuming they're going to have the same point spread function.
That was an assumption.
Yeah, I think that's reasonable. I mean, the whole slice thickness thing is different, right? Because it's in the cone direction. it's not an in-plane point spread function. It's sort of a different sampling in the
Mm.
in the cone direction. And so in many ways, it's just sort of a partial volume effect, right?
Yeah.
And and one of the things I'm not sure if you guys did it, I can't remember, is like if you have a small piece of calcium and you have a slice that's like this, and that calcium can move from one side of the slice to the other, you'll still detect it and it won't change the Hounsfield unit in that pixel, right? But it'll be a lot lower, right? So there's a size under which it just goes below, say 130 if that's your cutoff.
Hmm.
And then you just say it's not there, right? However, if you cut the slice in half, it can land in a single slice and be quite bright. However, it can also go right between two slices, right? So now you've got a little thing that's split between two slices. So it becomes a little more complex, right?
Right.
Yeah, I think you have the slide up right now. We kind of looked at that primarily because in one of the simulations we saw that the score started to go up as the partial volume effect um, started to go away. It started to become less of an issue. And then we saw this one example where the slice thickness got smaller and our score decreased, which led to what we've kind of coined. I don't know if this is a proper term, but this whole phase artifact thing, where the calcium, you don't know exactly where the calcium is starting and ending in relation to where you're taking your slices.
Right.
And we see on this screen that at thicker slice thicknesses, this kind of the importance of where the calcium is with respect to the slices is more important for these thicker slices than they are for the thinner slices.
Especially for the things that you're looking at. The things is it all depends on the size of the thing to the size of your sampling grid, right?
Yep.
Yeah, yeah. So, okay. Let me see what questions we have out here from the gang. See if I have. Uh, if the CT dose were kept constant, would the same trends in the calcium score still appear?
The answer would be no, because you're kind of baselining your HU to the background levels. And so as your noise increases with thinner slice thicknesses, then your background kind of just volume goes up. So all your calcium scores would decrease proportional to that. Um, to kind of negate that and make this more of a fair comparison, we did take that assumption that the dosage was done appropriately to keep the noise ratios similar through all the slice thicknesses.
Right. Um, and then so the other thing is like, what is the relationship between the Agatston score and say calcium volume? And does one make more sense than the other? I guess this is kind of an editorial comment.
Yeah. If you could go back to one of our first slides, we show the calculation of the two in comparison. Yeah, it's on the top right there. So the Agatston score is the area of pixels that have a Hounsfield unit above the 130 threshold multiplied by a density factor based on how, so actually, sorry, if you go back another slide, I think I have the density factor table too, on the left, multiplied by the density factor, which is like how dense is the calcium, and then you're adding that over all of your slices. So that's the Agatston score. The problem with that is as you scale your slice thickness down, you are going to be adding up a whole lot more pixels.
Right.
And so the Agatston score is a uh, probably less impartial to slice thickness than volume because the volume score is just the voxels regardless of the slice thickness size.
Right. Right. I think volume score probably makes more sense, but Agatson's been used for generations, right?
Yeah,
So
it's weird.
yeah, it's a weird thing. It was actually written on a napkin by Agatston. So okay, thanks a lot. That's great, guys. And okay, we're gonna move on. to our next project. Okay. And this is group 11.
Um, Hi, hello everyone. We are group 11. In this project, we're gonna explore the use of N-unit model and also SAM model for segmenting COVID-19 long lesions on the CT images. So N-unit model is a salient model that is specified for medical image segmentation, and the SAM model, the segment anything model, is a promptable foundation model that is used for image segmentation. So the promptable meaning that the users can feed the model with different types of prompt, like bounding boxes, like tags, like points, and then the model can generate masks condition on those different types of prompts. So in this experiment, we fine-tune the unit model with part of our data, but we didn't fine-tune the SAM model because of like time constraint and computational resource constraint. We evaluate the segmentation performance of the two models using three different metrics: the depth similarity coefficient, the internet over union score, and also the 95th percentile Hausdorff distance. So we can see that clearly from the table. The N-unit model, even without fine-tuning, outperformed the SAM model in all the three different metrics. Um, um, I think meaning that the fine-tuning is still very crucial for accurate medical image segmentation. We also explored the use of like a larger number of points as prompts in this experiment, but it only yielded very minimal improvement in the performance. And we show the mass comparison of two scenarios like on the right side. Yeah, so the upper right is the mass comparison for the unit model, and the lower right image is the comparison of masks in the SAM model scenario. Okay, thanks.
Okay. So the SAM model, when you say you didn't have time or you didn't have the resources to like feed it something to locally train on, was that the kiss of death for that model? Is that the reason it performed so badly?
Yeah, I think that could be one of the reasons. Yeah, the thing is, it's not very easy to fine-tune the model actually, because well, kind of in this experiment we kind of explore we kind of utilize a pre-implemented automatic pipeline that is available from the transformer library. So in order to kind of to fine-tune a model to perform well with this pipeline, you have to actually incorporate the whole pipeline in the fine-tuning process, which is not that easy. You cannot just like use one type of like prompt to fine-tune the model and then use like a different type of prompt when you do the inference. And that way, like the performance is really bad. We actually experiment with that. We actually experiment with kind of like a pre fine-tuned model, but it didn't perform very well.
Mm.
Uh, yeah, so
And then, so I mean, I've had colleagues who've also with our data tried this segment anything model, and it never wins. It doesn't. I don't know if anyone out there can defend it and say, "Oh yeah, this thing works great." Doesn't what does it work great on? Do you know?
yeah, I think it's a complex topic. Uh, uh, how to like fine-tune the model to perform really well in the medical image segmentation scenario. I think it has a very good like performance in the natural images,
So like
but
identifying cars and things like that out of
yeah,
videos or something.
yeah.
Okay, and so here's a question from the group. What does the NN unit change compared with the vanilla UNet, and how does that make it so much better for these tasks for medical imaging segmentation? Because this one has obviously come up to the forefront in all of our when we go through various models. This one seems to perform really well on lots of complex tasks in CT.
Okay, yeah. Can you hear me?
Yes, yeah.
Oh, okay. I think the UNet it can automatically configures the training pipeline based on the dataset properties like it can analysis the image sizes and maybe the class distribution or
Yeah.
so it actually use a UNet architecture and there are different types like 2D, 3D, and they can automatically use the batch sets or the patch sets. It just don't need you to train the set use your parameters. They can just you can just set up the processing steps and you use their prompt use their uh, sorry. You can so you can just so it can dance through the fixed heuristics. It's derived from the large scale experiments across different data sets in the medical segmentation competitions. It can get uh, very good output compared with the uh, SAM model or because we can see in the first line of the table, it is used the pre-trained weight. Its result is not
Not great.
it's not good. But in the second line, actually we fine-tuned with our own data set. We take 90% of the data set to train and do the validation, and we just use 10% to do the test.
I see. Okay. So it seems to be more adaptable.
Yeah.
And okay, Tom, do you have any questions?
Yeah, I guess the general question I know to not you may not have looked at it, but so when you did the fine tuning, I guess it adjusted all the weights. Do you have a sense of what features it sort of was able to pick up that the original unit could not?
What features?
Like perhaps there were small independent lesions that were picked up by the NN that weren't originally picked up or something, or it extended 3D volumes.
Or yeah,
Um,
another way of phrasing the question is, yeah, when the how did the original unit fail in ways
Yeah.
that the fine-tune unit fixed? Like getting to Dr. McVeigh's question, was it better able?
I see. I think because we use the pre-trained weight on task 115, and it's also a COVID-19 computation. The result is also from a computation. But they use the 3D figures, and I think, for example, because there are much differences between the two data sets, like the slice thicknesses, or the resolution, or the scanner types. So I think this maybe affect the final result of the appearance of the lesion.
Okay. Any last questions, or do you guys want a last statement? We'll move on otherwise. Okay, thanks. And then UNet still reigns supreme, I guess. And
Yeah.
continue to use it. Okay, so we're moving to group 18. And so this looks like it's,
Hello.
hi. Yeah.
Um, yes, so we're group 18, and our objectives for our project were to compare fan beam and parallel beam CTs in terms of sampling and magnification, spatial resolution, uniformity, and reconstruction accuracy. Our ultimate findings were that parallel beam geometry ensures uniform spatial resolution and predictable aliasing, but it's less productive as it's a lot more slow. It's more better for like, or it's best for analytical or like kind of analytical studies. And then our second finding was that fan beam geometry provides faster acquisition, but it does require a little more mathematical correction because of its non-uniformity. Our third finding was that rebinning algorithms effectively correct those sampling irregularities in fan beam CT. And then our last finding was that blur analysis confirmed that both focal spot and detector size contribute to image degradation, but fan beam geometry magnifies peripheral blur.
Terrific. Okay, so I'm just gonna run through the slides again. You made some nice slides here, yeah. Okay,
Thank you.
yeah. So this is the explanation of it. I'm just reminding myself what goes on in here. Okay, yeah, these are nice explanations. Yeah. So this confused me though. So this is the full width at half max for the
Yes.
parallel versus the fan beam. And I suppose what I was expecting to see as a function of radius. So this is you're measuring the full width as half max as we're taking an object and moving it from the center outward, right? And then remeasuring full width at half max. Is that how this was done?
I think what this does is it graphed what the full width at half maximum was. I don't think it was for a single point. I think for this one, I used a Shep Logan Phantom, and we found that like in the center, because of the magnification, it was a little bit higher than we expect because of oversampling. But then we also found that like towards the mid periphery, it kind of balanced out between oversampling and the angle. And once it moved further out from there, it spiked again. I think we were trying to demonstrate the uniformity between parallel beam and fan beam.
Ah, and so this blue curve was measured on this at the same points on the Shep Logan Phantom
I do
as,
believe so.
as these points. I see. And so the full width at half max came up 9 pixels on the Shep Logan. Do you remember where you made the measurement? If I bring up the Phantom, do you know where the heck is it? Or
I
do
think it
you
was.
later do you show the
I think it was
Phantom?
a. I don't think I showed the Phantom in this one because I couldn't quite get the code to work to include both at the same time, so I just had to graph up.
Okay. Okay. I have to say I'm if somebody brought this as a result, I've got to say I've got my doubts, right? Because things rarely go like this. You have like brrr, everything perfect on one thing and then another one that's a little bit random. So I'm not quite sure that I would classify this as the resolution change as a function of distance out towards the outside.
Oh, I just wanted to add, I think when we were looking at this image and like graphic, how it kind of made more sense to us was that the system geometry of the parallel fan beam stayed constant. And so then comparing that with the fan beam, the central rays experienced higher magnification, which produced a smaller full width at half max, which makes sharper detail at the center of the image. And then the periphery has a larger full width at half max, which results in more blur. So I think like at the time, that's kind of how we were viewing it. And it did help us, I think, understand the dynamics a little more.
Okay, so yeah, I guess it would be good if if also on this slide you had the picture itself with whatever the profile was. When you do the full width at half max, did you, it was an edge and you measured it off an edge in the Shep Logan Phantom? Is that right?
I believe so. I think it went piece by piece across the Shep Logan going from the center out. I don't know why the graph started so low for the parallel beam. I think it might have been an issue with the for loop that we had because there were photos associated with it, or there was like the phantom associated with it, but it I think I messed up somewhere in the for loop and it kept giving more and more pictures and I just cut them out because I wasn't sure how to correct that.
Okay. All right. It sounds to me like we probably want to go back and look at that and see what went on there. And so this sampling density in Nyquist, right? This was changing. That's cool. Um, so this is focal spot and detector blur. Ambient recon base. Parallel recon. Okay, so this is fan beam recon with a different focal spot. Is that what we're looking at here?
No, for this one we did a reconstruction of the fan beam and the parallel beam. I don't know why the phantoms came out so dark. I think I tried fixing the color mapping, but it didn't quite hit. But what we were trying to demonstrate was that between fan beam and parallel beam, the parallel beam, which is the one on the bottom, kind of does a uniform blurring. It's hard to see, but it's very fine. You can kind of see the colors in the center kind of blur out.
Yeah.
But the one above is for fan beam, and it shows kind of like a peripheral blurring.
Okay. And this is, what are we changing here? So this is 2 pixel. And then if I go back to this one, it's a 0.5 pixel. Is this, and that's a 2 pixel. I guess I lost track of what actually was being done here.
For this one, I think we were increasing the detector size to kind of induce that blurring effect.
I see. So that's this one, you're increasing the detector size?
That one might have been the focal spot, yeah, making that one bigger actually.
Can I
I
ask
think the next one is the detector.
Yeah, I just had a general question. So, I mean, looking through your code, there's a lot of code, which is great. But it seems like you used the radon and iRadon for the parallel, and then it seems like you either wrote your own code or got some code. There's a lot of code for the sort of for the fan beam, and I'm just curious why did you compare that to the MATLAB fan beam code, and like what was the decision process in terms of using the standard MATLAB for the radon, for the parallel, but using sort of other code for the non-MATLAB code for the fan beam.
At some point, I started trying to figure out which one was doing rebinning and which one wasn't, because towards the end of the project, we started trying to compare the non-rebin version of fan beam reconstruction and the rebin version. So some of the code partway through might have used a different version of that to accommodate for those investigations.
Okay, was there a reason not to use the MATLAB sort of standard fan beam code though? I mean, what was the reason not to use that? Just as a sort of a sanity check.
Kind of had a difficulty working with it. I did get a little bit of help from ChatGPT to try to like troubleshoot some of the code, and that ended up working a little bit better than the MATLAB version.
Okay. And then one question is on slide, I guess 11, the reconstruction of fan beam geometry, where the rebinning. Can you maybe comment a little bit on what we're seeing in that one?
I'm sorry, can you give me that slide again so I can?
Slide 11. So I think if you keep going, there's one where there's really images that look very blurry at sort of towards the end. Just keep going, keep going, keep going, keep going. They're right there, that one.
Okay.
Yeah, so with the rebinning, can you tell me what's going on here? Just like, is it a scaling issue? Yeah.
Yeah, so I can go ahead and explain that. So I guess it goes without saying that perhaps we might have added a bit too much noise, which is why the images are so glowy. But essentially, what we were trying to convey in this simulation is that the left image with no binning reconstruction, um, it shows that without rebinning, the artifacts due to band geometry and sampling are distributed as like softer streaks and blurring around the object, and you see kind of a smoother fall off at the edges. Whereas the image on the right with rebinning shows basically interpolating the fan beam data onto a parallel beam geometry. And then this adds additional smoothing, which can further suppress the noise. But you do kind of see that there's a sacrifice between spatial detail for a more uniform image.
Okay, so you think it's just too much noise?
Yeah, we definitely added a little bit too much noise on that one.
But it's surprising though that it doesn't look noisier, it just looks blurrier, right? So, but I guess that makes sense. That it would look blurrier if we're rebinning, you're just like making your bins larger, right? Is that right? Is that what's going on here? I don't know. Depends how they do the rebinning, I guess. You know, how much is in there. All right.
Yeah, I think to my understanding is like the big kind of ellipses to the left of that image was just kind of like a uniform shape, whereas after the rebinning, you kind of see a little more add like a little more detail in terms of what the image actually looks like. And then you do see post rebinning that it's actually not a perfect kind of circular shape like in the left image. But definitely, if we could make any corrections moving forward, would be to reduce the noise for sure.
Okay. And so these are profiles through a concentric. So there's three concentric rings. Is that what this phantom is? That's the profile through the middle.
Yeah, I should have added a picture of it, but I like the kind of like structure of the slide. So I looking back, I should have put it back in there, but these are the vertical profiles of three concentric rings so that we could demonstrate the changes in fidelity to parallel beam after it was rebinned. We wanted to show that certain areas were compressed and widened as a consequence of fan beam geometry.
Okay. And so this profile of that thing is the parallel, and this is the fan no filter, and this is fan rebinned, right?
Right.
Okay. But this is a pretty spectacular function in terms of what is going on here. It doesn't, I mean, something's going on, right? If this is the reconstruction of this object, there's some other thing going on here. Uh,
We didn't do this one with noise. We wanted to kind of demonstrate it as cleanly as possible, but
right, right. Well, I agree. It doesn't look like there's noise on it, right? It looks pretty clean, but it does look like there's a lot of spatial blurring.
Constructed a three-ring phantom in MATLAB and applied a direct fan beam,
I hit play by
rebin,
mistake.
and parallel beam geometry. And the parallel beam vertical profiles, the impulses.
There we go. Okay, great. I think, yeah, we gotta move on. Sorry. Okay, thanks so much for that.
Thank you.
All right.
thank you.
And we go 3, 4 here. So we're on to team 17.
Hello.
Hi.
Yeah, so we are team 17, and my name is Matthew. And our project was to do motion artifacts and simulate them. So motion artifacts can distort the underlying data and potentially prevent appropriate diagnoses. We can imagine this becomes a challenge where it is difficult to keep an object still, such as a heart or a moving target. Although technological advancements have significantly increased the rate of imaging, and thus they are reducing the artifacts, it is still interesting to demonstrate how these effects may manifest in the clinic. So here we simulate motion, rotation, expansion, and random jitter of a brain CT, and our results show that these produce unintuitive distortions in the underlying data. And yeah, Graham, if you have any.
Yeah, no, I think that's good.
Awesome.
Okay, great. Um, so this is interesting in your choice, I think, of motions. The cool thing was the motion amplitude that you guys chose to investigate is realistic, right? They were fairly small in terms of amplitude.
Yeah, we didn't want to go too over the top with it. Maybe just something that you might see, like a patient shifting slightly.
Yeah, if
Right.
anything, I think they're extremely minor, and yet you can still see very clear artifacts. So it felt like why do more, you know?
Right. I mean, there's two arguments. One is when you do bigger motions, you can see the how CT deforms an object. It's
Hmm.
not just a simple superposition of images of that object in different places. That's not what
Hmm.
happens, right? So in that sense, when you actually the other group who aren't presenting who put these large motions and you can see these cycloid shapes and all of this stuff that happens from CT, and it's quite complex, right?
Yeah, I played around with it in like a simpler simulation of it with just like pixels moving across the screen. And yeah, they produced large, not very intuitive streaks.
Exactly.
And yeah, unfortunately, like if one of the questions is like how can you reconstruct an image if there was motion, I didn't play around with it enough to get a good intuition for how I could attack this problem besides maybe throw some sort of network at it
Right.
and hope for the best.
Right. Well, you
Mhm.
can attack this problem, but one of the questions that came in, and this is another question, is like you you did these really nice simulations in a clear image so that you can see an object and see what happens to that object, its fidelity. And what happens if these motion models are superimposed on each other, right?
You mean like there's two types of motion at the same time, like rotation and
Right. Or
translation?
or which can happen. It doesn't happen in the head. It happens in the body, though. You have different motions in different parts of the field of view, right?
Mhm.
Then it's like, how do you correct that data?
Yeah. I mean,
You can imagine how you correct, say, this um, rotation, right? Somebody's head. So if over time it goes from this position and clicks over to that position,
mhm.
you know, can you guys see me, by the way?
Yeah,
Yes.
Oh, thank good. Okay, so clicks over that position. Um, you can imagine the deformation that happens to the sinogram, right? And you could just like take that rotation out.
right.
If I know the rotation or the movement, yes. But if I don't, I don't even know how to attack that.
Well, that's iterative algorithms.
Yeah, I
Mhm.
could see an algorithm like detecting the nose and kind of re-rotating it, something like that. But you're right, if there's multiple motions, then it becomes a lot harder
Right. But if
if two
it's
things are moving differently.
yeah, if it's a simple rotation of the head, even for a fraction of the views you took, you could say, I'm going to assume it's clicking at certain degrees per view,
Mm.
and I'll just correct for that, and let's take a look at the picture. And you look at the picture, and it gets worse or it gets better, right?
Mhm.
And you just keep iterating until you move into a correction that's better. But when you guys were evaluating, let's go to your movie. It's like 1, 2, 3, 4 here. This was actually fun. This is really cool. I like this. Thank you for doing that.
Yeah,
That's
of course. I
yeah,
liked it too.
yeah, it's really cool. This like that, right? that's a non-intuitive artifact, right?
Yeah.
That you
Oh,
get.
and something interesting I noticed was if the motion was very fast, but then it settles into another position, then it remains relatively clear. Like there's a lot less streaking.
Right, right. But this type of artifact where you have this dark shaded thing here and
Hmm.
then a amplified brightness or sort of shading over here. This is super important in, for instance, coronary imaging, where people are trying to identify dark Hounsfield units as fat or inside a lesion, you have a lipid-rich, quote unquote, lesion. And so your Hounsfield units are lower in those regions, but they're also lower because the damn thing moved, right? So you have to take that motion out. But anyway, and now when we're looking at yeah, let's take a look here. So we have the pretty subtle stuff going on here and here. So when you did these numbers, RMSE and SSIM, did you do it in this field of view right here or in the whole picture?
Just in the whole, yeah, we probably should have done it in the ROI as well.
Okay, okay. Yeah, so probably makes sense if you have a target like this to ask, how does it change? It's pretty subtle, right? In a lot of these. But this is realistic, right? So this is breathing. This is, I guess you got somebody. How was this something moving up and down sinusoidally or something? Distortion?
So it was expanding and contracting
Oh,
by, I
that's
think
right.
it was 0.1, so to 1.1 or 0.9. And then it was also moving up and down very
Up and
slightly.
down. Yeah, yeah. And so yeah, you can see it kind of destroys the detail of the actual target, right?
Yeah.
And so so if you wanted a metric to test as you're making corrections to your sinogram, which is the next step to this, right? It's like, can I look at the sinogram and correct it? You need a way to sort of close in on this thing. Um, okay. Uh, cool. Tom, do you have some questions?
No, I don't have any questions on this one.
Yeah, that's pretty cool. All right, let me go to the gang here. So were there motion artifacts you observed during your simulations where fan beam can actually yield better results over parallel beam?
Um, I did not notice any. I would say that, so I mostly highlighted the step showing things being, more spatially complex. Everything
Mhm.
that I saw was either very similar or more spatially complex. I do know though that uh never mind. I was gonna say something that's not really relevant.
Okay, cool. Um, great. Well, this is good. Thank you very much for doing all these good simulations. I think these are really useful in terms of understanding how this stuff falls apart under motion. And it's something that now, like we have, as you get to higher and higher and higher resolution, so we have pixels that are like 0.35 by 0.35 by zero point 0.4 millimeters. Anything's moving at that resolution, right? So in the human body. So I think if you want high resolution pictures at that pixel size, you need to do motion correction. Okay, cool. Thanks, gents.
Thank
So
you.
move on. We're gonna
Thank
go
you.
to one here. Okay, we're comparing filtered back projection and inverse Fourier transform.
Hi everyone. Can you hear me clearly?
Yes, we can.
Okay,
Thanks.
perfect. So today our project basically focused on comparing the two fundamental methods for CT image reconstruction. So filtered back projection and inverse Fourier reconstruction. So our goal was to simulate both in MATLAB using the Shep Logan Phantom and generate projection data or sinograms to evaluate accurately how each method could reconstruct the original image. So theoretically, both are based on the central slice theorem, which links 1D projections to lines through the object's 2D Fourier transform. But in practice, they actually behave really differently. So FBP applies a frequency domain filter before back projecting. So that would basically correct all the non-uniform sampling and enhancing edge details, while IFR reconstructs directly from the frequency space. So we find that it's more sensitive to errors and noise. And as shown here in the middle, where we have our results compared to the original, the FBP image is sharper and truer to the original, while the IFR shows a lot of blurring and streaking artifacts. So quantitatively, when we put in the numbers, we found that the FBP achieved a PSNR, or peak signal to noise ratio, which basically is similar to measuring the image compression, so a lower distortion level of about 34.5 decibels compared to the 24.8 of IFR, and a SSIM, or structural similarity index, of 0.96 compared to the 0.79 of IFR. So it basically just confirms the theory or the overall comparison that you'd find that FBP does produce superior images. So in summary, you could say that we just confirmed that FBP remains more robust and practical, and IFR just highlights that even though the theoretical foundations of CT imaging and everything alludes to IFR being a viable alternative to FBP, I think it needs to rely maybe a bit more on the integration of machine learning or convolutional neural networks to correct the lack of fidelity that we find, or maybe the use of non-uniform fast Fourier transforms to make up for whatever we lack in those streaking and blurring artifacts.
Okay. Tom, I'll start with you. Do you have some questions?
Sure. Yeah. I did have a question. So you showed that the IFR didn't perform as well, and you suggested some changes that could be made to make the IFR do better. And it seemed like in the code you might have tried some of those changes, but then it didn't seem like you presented them, or the presentation didn't seem to have them. Can you maybe comment on that?
Yeah, so basically what we did when we designed our group project was we all tried to attempt designing our own code. So I believe that might have been my code where I gave it an attempt. I kind of just put it in AI and I thought I would add on because coding isn't my strength. So I thought I would just give it a try and see what results I could get from maybe asking AI to like build upon improving IFR. The only thing was the results that I got were significantly worse. So I felt like it was not worth pursuing right now. And I don't think I have the computational power to, look into non-uniform for fast Fourier transforms yet. But if I had more time and like I had the luxury of maybe learning the code and build upon it, I definitely would have included that in it. I think I had just sent that to the group. So we just added it on, but I didn't feel it was noteworthy enough because it just didn't prove my point. I couldn't improve on it. So
Okay,
yeah.
great. Thanks. That makes sense. Okay.
Yeah.
So I think the comparison here is between FBP, which is, I guess, more straightforward to implement because you don't need to do much stuff, right? You don't need to density weight or interpolate data onto a Cartesian grid or do anything like that. I think though the IFR that you've presented here isn't, I think you can take it a little further to make it more representative of what you could expect to achieve, right?
Mm-hmm.
Right? So that if you don't do anything or you just do a simple IFR, you're going to get some of these artifacts. But with a few simple steps, you'll get a lot closer to a real picture, right? And so it in some respects, what you've demonstrated here is, hey, if you're going to do IFR, you got to be ready to do a whole bunch of other things before you do the FT to go back and get the picture, right? I think, did you guys have something in here about a Sino CT data set? Is that you guys? Is that somebody else?
Yeah, that was us.
That's you guys?
I found,
What's that all about?
so we originally tested both the IFR and the FBP on the Shep-Logan phantom image. I wanted to see if I could try that on a real sinogram if possible. So I found like a Stanford CT data set.
Oh, okay.
Yeah, so it was just publicly available CT scans. I believe that for like the entire 3D volume, there was around 40 slices. So I selected one of the slices and tried to apply kind of the filtered back projection onto the slice and see what we get. It wasn't working so well the first couple times. I wasn't really seeing anything except like a dot in the middle. But with a little bit of pre-processing and a little bit of AI, I kind of got to reconstruct what we see on the right. But yeah, I wanted to see if we could try this on like a live, like a sinogram of the patient's head and just see what comes out of it.
I see. So you started here with a sinogram with obtained on some clinical system or something like that. And they gave you I guess a picture of what it should look like when you reconstruct it. Is that right?
Yeah, when you like stack all the 40 slices together, they had like a what the 3 volume should look like
I see.
when we reconstruct.
But then after that, that data was not used to then go in and look at these other statistics like that you guys measured here.
No, 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 no. I
Okay.
think we probably could have done that, but we didn't go that route. I kind of just did this just to scratch it and just see what it looks like if we
I
apply
see.
this to real data.
Okay. And okay. Yeah, so all of these things, yeah, you've discovered that you should probably do when you're doing IFR. And I guess um yeah, I guess there isn't a heck of a lot of reason
Yeah,
to.
I think the main thing was because our project topic basically covered on the MATLAB investigation of it. We kind of just focused on the technical aspects, and that's when we kind of decided to look more into probably what could be further implemented. I would have liked to maybe go into Python and try my hand at a CNN to, apply the data and see it. But again, because kind of even while filming the topic and content, we felt like it was a lot of information foundationally to work on because it's a preliminary concept that our topic covered. But definitely, if we had more time, or maybe even just out of interest, looking into the research that's being done right now with MRI techniques in specific, this particular publication, I just found that there's a lot of potential for applying a convoluted neural network to, see if it could make up for what IFR doesn't do with the noise, and the missing angles in essence is what causes that streaking and artifact blurring. So applying an iterative type of network that learns with more data that we put in, I felt like it would be a really interesting approach, but it felt like a lot to bite off, like given that it's our first project and also that we're focusing with MATLAB in particular. But yeah, I guess it was kind of hard to put that in the PPT in terms of like content, which is why it's more simplistic. And we tried a lot of different things, like Dr. Tom had mentioned, like we tried, but then it just didn't stick. So we never put it into the final presentation because we wanted it to be crisp enough for it to demonstrate that we got the concept. But yeah, that's kind of where we fell with our presentation. Yeah.
I'm sure if you had enough examples, of CTs in polar coordinates and enough true images, you could train a network to make
Yeah.
that transformation with the appropriate resampling and everything. It would probably figure out how to do it eventually. Okay, great. Okay, thank you, team, and we'll keep trucking. Okay, we have. I guess this is group 12. And we're looking at perivascular adipose tissue. Okay.
Hi, yes. Can you hear me okay?
Yes, we can.
Great. So our project took a more clinical perspective. And as you mentioned, we wanted to look at the correlation between the Hounsfield units of the perivascular fat with patient size and with coronary calcium volume. So just to remind everyone, PVAT is the adipose tissue that surrounds the coronary arteries, and it's a known marker of local inflammation. And coronary calcium, like the name suggests, is calcium buildup in the coronary arteries. And it is a byproduct of previous reparations and therefore is a risk factor for heart conditions. So we searched the literature, which showed that obesity increases, of course, the volume of the PVAT, but it also alters the composition of the adipose tissue. And furthermore, it promotes inflammation. And so based on this, we hypothesize that higher Hounsfield units values of the perivascular adipose tissue would correlate with larger patient size, as well as with a higher coronary calcium volume. So to test our hypothesis, we looked at 100 non-contrast CT scans of the cardiac region. And from those, we estimated the patient size, the calcium volume, and the Hounsfield units of the perivascular fat. And to look at the correlation, we calculated the Pearson's correlation coefficient between these variables, as you can see in the plots on the right of the screen. And our results show no correlation between the mean Hounsfield units of the adipose tissue and the coronary calcium volume. And we did find a weak negative correlation between patient size and the perivascular fat Hounsfield units, which was surprising. And this suggests that actually smaller patients tend to have a more inflamed fat, which, yes, when sort of against our hypothesis.
Okay, so Tom, do you have any questions off the bat?
No, I don't.
Okay, so let's get the bigger version of your results here. So just to review, here's what you're using. You're using, I think, did you take the perivascular fat in one slice, right?
Yeah, I took it in one slice
One slice
around
per patient.
right there, pretty much on every single patient. It was a different slice, obviously, number for every patient, but I went through each
Right.
patient, just took one.
Right. All right. And then the calcium was done in an 8 centimeter stack for that patient. So you looked at all that patient's calcium.
Yes.
And
And
then
I did a freehand ROI around both coronary arteries to see if there was any in either. And then I had it go up 4 centimeters from the slice that I selected and down 4 centimeters. So then we had an 8 centimeter stack so we could get the majority amount of the
right.
coronary calcium in the arteries.
Okay, cool. And so here you go. Here's your first result is the calcium volume, which is you just counted up all the calcium above whatever your threshold was, which your
It
slice
was
thickness,
130.
say that again.
Sorry, it was 130.
130.
Yeah,
And your slice thicknesses were, I think, zero point 0.6 probably, right? 0.62.
I believe so, yes, around there.
Okay. And here's what you measured for the Hounsfield units and the fat. So you've got starting down here at about minus 115, so 120 to 110. So in each one of these blocks, you've got a fairly good number of people.
Yep.
And that's a pretty big range of Hounsfield units, right?
Yeah.
I mean, it's not like we're trying to figure out between a whole range of 10 Hounsfield unit differences.
No.
So that surprises me that it's this big, actually.
Yeah, there were definitely a lot more within the 90 to 130 range. And majority of the patients are around negative 104-ish
Here or
to
something.
105. Yeah,
Yeah.
that was the majority of the patients that I saw, but there were a few that were on the lower end.
Okay. And as we move this way, the fat, let me get this right. The fat becomes more like water
Yes.
because we're going towards zero. And that is associated with this inflammation or inflammatory response. Okay. And it is not associated in this 100 people with the amount of calcium that they've grown.
Not really, no.
Yeah, it doesn't look like it at all, right? So that is interesting in that you would expect there'd be some kind of relationship that you might
Yeah.
have more calcium over here, right? In that as you got to more inflammatory fat, you would see more calcium. Okay, so that's great. And yeah, you could try this with 10,000 patients actually, because there's enough calcium scans in the world.
Yeah, that was one of our things at the end, is one of our future things would be to add more patients and see if theoretically more patients would add any type of correlation, because obviously we only did 100 and we were doing it by hand. So even
Right.
100 was kind of a lot of patients.
A lot.
But also training instead of using MATLAB, training a model in order to run through
Right.
tens of thousands of patients could potentially create a correlation.
And so here we've got the effective diameter of the patient, and I think you have a picture of that back here. So it's
Yeah,
this.
right there.
Yeah. And so that goes through their heart.
Yep.
This is the diameter of their thing this way. Okay. Until you take the mean of the product of those or something, the square root of the product.
Yeah, because I originally had just done two separate graphs, one of the coronal versus the mean fat and one of the sagittal versus the mean fat, and they both really didn't show anything. So we were like, okay, maybe if we tried the effective diameter to show the like average size of each patient, that might show more of a correlation. And it showed more, but not exactly what we were expecting at all. We would expect it to be the opposite. So
the slope, you would have thought, given people who well, if they're bigger and they're more fat or whatever, you're
right.
saying if they're bigger, they probably would be in the more inflamed group, which is this
Right.
group, versus this group, which is the more straight up fat.
Exactly.
We did find that the data was right skewed when we put like we ran a simulation and we found that it was right skewed.
Like this?
So yeah. So we would just need to have more patients to hopefully get more of like a uniform data set and then run it again and see if those correlations hold true.
Okay. Um, yeah. And so is there a hypothesis for why this could be true just the way it is?
We thought that maybe because CT imaging might have like more of a difficult time with larger patients,
Mhm.
that could have contributed to the data we found. I think that's kind of what we speculated.
So bigger people would cause uh, it could cause more beam hardening, right?
Yes.
Such that your Hounsfield units in the central part of a disk, like if you just look at beam hardening in a water cylinder, you don't correct for it, right? What you get is a dip in the middle of the water cylinder. So the Hounsfield units go down.
Mhm.
And so here you're saying if your effective diameter of the patient gets bigger, there's more beam hardening, and so you're going to see lower Hounsfield units in bigger people. A trend towards that way. Physically, that could be what's going on here.
Yeah, we don't have like an exact hypothesis, obviously, for why it would trend this way. But I will say when I was going through the CT scans, particularly the larger patients, I noticed it was really difficult to find areas, like really strong areas of perivascular fat, because they just had more fat elsewhere. So it was more difficult. I would have to zoom in really far and change the contrast a lot so I could find regions of fat, because I obviously didn't want to get any other landmarks other than perivascular fat. And then when taking the coronal and sagittal measurements, there were a few patients that I actually had to throw out because they did not fit on like the image. So I couldn't even get an entire
Right.
coronal or sagittal width and depth of them.
Right. That's a
Did
big
you-
person, by the
Yeah.
way.
Yeah.
Was there just one person doing the measurements, or do you have a sense of how noisy these measurements are? Like if you had two people do them?
I did all of them.
You did all of them. Okay.
Yeah. So they should be like I used all of the same landmarks for each patient. We kind of decided that it was easier for one person to do it because we didn't want to have any discrepancies in how we were drawing the lines or the ROIs. So we thought it was easier to just have one person run through all of the patients and then we all did the analysis together.
Now, is there any correlation between the diameter and the calcium score, calcium volume?
We did not find any, but I did run that in our code. I think in the code it's in there, but I commented it out and we didn't include it in the presentation because there was no correlation.
Okay. So the next thing you would do, what do you think would that be?
Oh, you can go ahead,
Oh
Karina.
yeah, I was just gonna say I think we would need to include a lot more patients, and then what Maddie was saying earlier was train the model to run through it so we don't have to do it manually.
Mhm.
Because that took a lot of time. She had to actually like draw a circle on every single patient and measure. Um, so I think kind of that would be our next steps to see. The main thing would be to verify the correlations with more patients.
Cool.
Also, adding off of that, I did have a few patients that had devices implanted, and that exposed a lot of what looked like calcium because it was of super high Hounsfield units. So I had to throw out those patients as well because that obviously wasn't accurate data. So I had to filter through each patient to make sure that they had the axial image, two localizer images, and to make sure that they had no devices because that would have really skewed the data. So, of the patients that we used, all of them were screened. So, that was also a lot. So, making sure that all of the patients, if we did train a model, had all of these images and to make sure that none of these patients had devices because that really upped the calcium score, even though that wasn't necessarily calcium in the coronary arteries.
Calcium,
Yeah.
So back to um, Tom's point for a second here. So if you were to estimate, say this point over here,
Mhm.
um, and you measured in this patient, I guess it was 295, millimeters or something like that is the value. The error on that is probably pretty darn low, right? It's probably the size of this dot in the vertical direction
Yeah.
or something like that. The error in this direction where you are saying, okay, I've got a mean of just under negative 120.
Mhm.
And do you recall the standard deviations inside your circle? And is it like the size of this dot or is it
Yes, I believe it's plus or minus 5 Hounsfield units,
okay? All right.
just to ensure that we got the correct
Okay.
region. But yeah,
Okay, cool. Well, then this is could be real, right? This one. It doesn't look like anybody, who's relatively small has super low Hounsfield units. So interesting.
yeah.
Okay. Well, thanks. That was a lot of work for that one. But if you can, automate it, just like there's a
Yeah.
bazillion cases out there in the world that you could run.
Yeah, if we had some more time, that definitely would have been the way to go. But it was really interesting to see, like, we really thought that there was going to be a different correlation, and to see this was like, wow, that's actually really interesting, and I would have never guessed that. So it's kind of a cool project.
Yeah. It's always good when you get the opposite
Yeah.
of what you had anticipated. That's always more interesting.
Yeah.
And now you've looked at 100 cases, so you're sort of more comfortable looking at CTs. It's always good to.
Oh, for sure. I stared at those for hours and hours. I could tell you all about them now, I feel like.
All right, cool. Well, thank you very much. And thanks everyone for doing a lot of work on the projects, making it worthwhile. It was great watching them all. And I'm going to continue making update to notes and we'll come up with a final evaluation for the whole thing. And and then the next set of projects are due how long, Tom? Is it like, I don't know. It's
Yeah, I'll send out I'm making up the project assignment now. So we'll
okay.
post it probably Sunday night and then we'll go over it on Monday just to answer questions about how it'll look.
Okay, and if you guys have feedback, about the project process and the process of coming up with questions, or anything like that, please feel free to tell us, because we changed it around a little bit this year, and so we're looking forward to any feedback you've got as to how this can improve. All right.